So we've been looking at Taylor series, and we're going to look at trying to justify theorem one, which is that the sequence part, the an parts of the Taylor series can be generated by the nth derivative evaluated at the center c divided by n factorial. So we can do this to find the coefficients of Taylor series and the more simpler Maclaurin series. But we're going to try to justify this, and we're going to try to justify this using in the Taylor series context. So we're not going to center it at 0 necessarily, and we're going to center this at c. So this is my f of x function, okay, and I'm trying to find a Taylor polynomial. I'm trying to find a p of x, basically, that will mimic that function, okay. So there's some conditions to be able to do this. The function, we need to know where the center of this function is. We need basically a starting point to do this. So we need to know the center point here. That has to be known, a known coordinate. And secondly, the f of x must be differentiable at the center here. So we must be able to get the derivative and multiple derivatives at the center there. So what we're going to do first is we're going to just start with the p of x, or the power series, the polynomial series. And we're just going to use one term, build it up from the first term. So we're going to start with the first term of that polynomial. We'll call it p of x. And the first term we'll call, a naught. And, well, really a naught is just a constant. And basically we're just going to find the value of that a naught by just plugging in the c value. And that was going to be the f value at point c. So we need that point to start. And that was the first condition. But really, once we've built that polynomial, this is our polynomial right here. Okay, well, the axis is going to be right here. We can replace that with f of c. That polynomial is going to look like this. It's going to be a constant. So it's this line is going to be our function, and there's our p of x function. Not a great p of x function. Okay. In fact, it's a terrible p of x function because the only point it really does any good is right at the center. However, that's what it is. That's the very first term of our p of x function, and that's what it would look like. It's not a great approximation, but the nice thing is we can add more terms to this. So how are we going to add more terms to this? Okay, before we add more terms, what we'll do is we'll just keep track of this. Okay, so when n is equal to 0, our an value we've worked out to be f of c. Okay, it's going to be that point there. Okay, so at c, we're going to get f of c. Great. But again, that's not, the horizontal line is not a good approximation for that green function. So we're going to add one more term to this series. Okay, so we know that the first term is f of c. The next term, we don't know the coefficient, but we know the power series part is going to be x minus c. Okay, so the idea then is we just got to figure out what that a1 term is. Well, if you take a close look at this function, this is really just a linear approximation function, right? We know the center, c, and the x and y coordinates of the point of tangency. That's just going to be essentially the tangent line approximation to that. So that's just going to be my linear approximation formula. So then it looks like this. Here's my linear approximation. Okay, well, that's not great, but it's much better than what I had before. Now, this is the first two terms of my Taylor series, or my polynomial series, and essentially it's just going to generate a linear approximation function to this green line. Again, not the greatest, right? But it is the linear approximation. So what we can then say is, well, if this is a linear approximation formula, well, that must be the f prime at c. Okay, well, that's it there. So that means that a1 and f prime c are the exact same thing. Okay, so I'm going to then put in here 1, and we can actually justify another way. I'll show you in a second, but really that's the most straightforward way we can do it. a1 and f prime c are the same. Okay, so we're going to get f prime of c. Okay, that's my an value. And we're just going to check this. We're going to test this. If this is in fact true, then we can plug in c, right? and we should get f of c. So if I plug in c, I get c minus c, that's 0, and I get the polynomial value at c is going to be f of c. Yeah, that's correct. Okay, so we can make that justification, and that, like I said, we can see that already here. Okay, so there it is. We're up to 2 terms, and we have our linear approximation of that green function, whatever it is. And really we want a better approximation. So what we'll do next is we'll just add one more term. Okay, so we're just going to add one more term to this. So we know the first 2 terms are going to be f of c plus f prime c times the first power of the power series. And then we're going to have the second power of the power series and our a2 coefficient. So again, we kind of want to know what that a2 coefficient is. So what we can do is actually, and this is the trick, is we can actually find that a2 by checking the derivatives. And basically what this was a linear approximation. This is the quadratic approximation formula. So it's basically the polynomial series that approximates it with a quadratic. Okay, so it's going to be, whatever this quadratic is here, right? Okay, so there's my quadratic approximation formula. Okay, that's what it is. And I just want to basically find out what that a2 is. And I'm going to do that by differentiating this. And why am I differentiating? Well, to differentiate it lets me figure out what this a2 is going to become. So if I differentiate this expression, I'm going to get rid of the f of c. That's a constant. And I'm going to be left with f prime of c, because that's the slope on this linear term. And then when I differentiate, I get pa2x minus c. And if I want to evaluate this, I can say, well, what is p prime at c? Well, if I plug in c into here, that's 0. This is going to be 0 here. C minus c is 0. So I get p prime is equal to f prime of c. Well, my p prime and f prime derivatives match at c. Yeah, that's correct. I have the right polynomial. Okay, so if that's in fact true, I can then differentiate it one more time. Okay, actually I'll just leave that there. P prime at c is equal to f prime at c. Okay, and if the first term is true, I can differentiate it again. If I differentiate it again, I'm going to end up with 2a. This is a linear term, so it just ends up being a constant. 2a2 is going to be my p double prime, or my f double prime. Well, if this is my f double prime, okay, and we know that's true at point C, okay, well, then I can rearrange this, and I can rearrange it to make an expression for a2. My a2 expression looks like this. F double prime c over 2 equals my a2. Or I'm actually going to make a jump here and just say it's not over 2, it's actually over 2 factorial. And then by induction, I can actually generalize this for an. Well, I can say that an is going to be fn, the nth derivative, evaluated at c divided by n factorial. Okay, and this is maybe a little bit of a stretch. So if you're not sure about this, we can actually just do one more iteration of this. And again, why the n factorial? Well, some of you may be able to see why that's actually 2 factorial, because you can see what happens here. You times by 2 and you times by 1, right? And if we go to the next one, right, we can actually even further justify this. So this is really my conclusion. But if that wasn't good enough for you, we can just do one more iteration of this and add one more term. So here's my first term, my second term I've already established, my linear coefficient, my quadratic coefficient I've established as that, and then this is my third term, and I don't know what the a3 is. Okay, that's why the goal then is I need to solve for a3. Well, this would then be a cubic polynomial. Okay, it's going to be a cubic polynomial that mimics that function through that point. Okay, and this is my cubic approximation formula. Okay, and what I should do is I should just fill in my table here. When n was 2, I had f prime of c over 2 factorial. And I'm going to make this 1 factorial. And I'm going to make this over 0 factorial. Okay, and what we're saying then is we're probably going to get, for a third one, we should get the third derivative divided by 3 factorial. So let's see. So if I do this process one more time, here's my cubic approximation formula. I'm going to differentiate the first time, okay, and I can check, I can check this and I can plug in p prime of c is equal to f prime of c. Yeah, that's still consistent. Okay, if I can differentiate again. Okay, so now this constant here, okay, becomes, f double prime of c. I'm going to multiply this constant by 2 times 3 times a3. Okay, that becomes my linear term. Again, I can test my p double prime of c. My p double prime of c is going to be, well, that's going to be 0. So that's going to be f double prime of c. So my derivatives match for my p and my f, my approximation p and my f. And then I can differentiate one more time. And this is where we're going to see then, yeah, okay, if I differentiate one more time, that becomes my coefficient. This is the slope of my linear term, so that's my derivative. And if I want to solve for a3, okay, I can say that this is equivalent to f triple prime at c. The p triple prime of x is going to give us the same as f triple prime at c, and I can solve for a3. It's going to be f triple prime at the center c divided by 2 times 3, or 3 factorial. So I've got the same iteration going on for the next go. So then again, by further induction, in fact, we can justify our theorem 1 formula. And if we take a look at our table here, yeah, we ended up with f, the third derivative, divided by 3 factorial. And so thus we can justify theorem 1 using this kind of induction process.